Newton's third law today, what it is and just as importantly what it's not. This is one that just because of the language I think people get wrong a lot. So there is a chance that you have specifically been taught Newton's third law by a teacher who misunderstands Newton's third law. You may have been taught wrong about this. Let's get you straightened out. And this is the phrasing that I think is messing everybody up. For every action, there's an equal and opposite reaction. Action and reaction, those words, they are misleading here. Think about what a reaction means to you. Maybe somebody says something and then as a result, you say something else. You react to what they say. Or you hear a loud sound and you flinch as a result. Those things are actions and reactions, and they are not at all related to Newton's third law. And so I think our everyday experience with those words of action and reaction skew our thinking on that. Combine that with maybe some folks who think they know what they're talking about, telling you Newton's third law is about things like that, and we can easily get confused about Newton's third law. But action and reaction, let's get rid of those ones altogether. And instead, we're going to state it like this. When two objects interact, they each experience a force. Those two forces are equal in size, opposite in direction, and simultaneous. And this is how we're going to think of Newton's third law. Two forces, two objects, forces are equal in size, forces are opposite in direction, forces occur at the same moment. So we're not talking about two different actions, one happening after another. We're not talking about two events. We're talking about two forces. And specifically, we're talking about two forces that are each on one object. One object gets one force, the other object gets the other force. When two objects interact, that interaction is what we call a force. And that interaction has an effect on each of the two objects. So think about like a ball rolling into another ball. Each of those balls has some change to its motion. They each experience a force. Or a person running into another person, say football players. One person is tackling another football player. The person getting tackled isn't the only one whose motion changes. They're not the only one who feels that force. Now, if you hit somebody, you feel that hit. And you're not feeling a force that's acting on them, you're feeling a force that's acting on you. You can't feel forces that act on somebody else, you only feel them when they act on you. So a few examples next of Newton's third law pairs of forces. And that's the terminology we're going to use instead of action-reaction forces. So first let's think about this box that's sitting on the ground here. We'll think about the forces that are acting on the box. And so we've got a downward force from gravity and an upward force that we call the normal force. Two forces, those are going to be equal in size, they're going to be opposite in direction, and that has nothing to do with Newton's third law. We can't do anything with Newton's third law until we identify pairs of objects that are interact and cause those forces. So the normal force and the force from gravity, those are not a Newton's third law pair. That's not an action-reaction pair. Instead, let's think about pairs of objects that are interacting here. For the normal force, what causes the box to experience a normal force? Well, it's in contact with the ground. And so the ground is an object and the box is an object. They are interacting. And as a result, they each get a force. And so we could have a Newton's third law pair here where one is the normal force, and that'd be from the ground on the box. And the normal force from the box on the ground. So the box is pushing down on the ground is getting a downward force from the box. It's not a gravitational force from the box that pushes down on it. Gravity pulls the box down, but that's not an interaction with the floor, that's an interaction with the earth. The earth is pulling down on the box. And so that downward force from the box on the ground, that would be a normal force. So we have two normal forces that make up a third law pair. What about gravity? Well, gravity, like I said, is an interaction with the earth. The earth is pulling down on the box through this force of gravity. So we'd have force of gravity, and that's the earth pulling on the box. The third law pair for that is the fact that the box exerts a force of gravity on the earth. And so that would be box on earth. The box pulls down, or sorry, the earth pulls down on the box pulls up on the earth. Those two forces are equal in size and opposite in direction, and they occur simultaneously. The same goes for the two normal forces. If there's a 10 Newton force upward from the ground pushing on the box, then there's a 10 Newton force downward from the box pushing on the ground. The ground experiences a downward force, the box experiences an upward force. Inevitably, at some point, I get the question, if third law pairs of forces are equal in size and opposite in direction, don't they just cancel each other out? Well, no. We can tell that they don't because things change. So if third law pair forces canceled each other out, then every object would always have a net force of 0 on it, which means that no object could accelerate anywhere in the universe. Everything in the universe would be traveling with constant velocity, either stopped or moving in a straight line at a constant speed forever. That clearly doesn't happen, so it must be possible to have an object that isn't in equilibrium, that doesn't have forces that just balance each other out or cancel each other out. But how is that possible? If every force has a third law pair to it, then shouldn't they just cancel each other out? Well, no, because they don't act on the same object. So let's say we have these two boxes, a red box and a blue box, and they're connected by this rope. And so ropes carry what we call tension force. And so if I drew a free body diagram for the red one, I would see that I have a tension force, we'll call that Ft, to the right. And if I drew the free body diagram for the blue box, I'd see that I have a tension force to the left. And those two forces would be the same size, they're in opposite directions, they happen simultaneously. It's an interaction between the red block and the blue block, indirectly, using the rope to allow that interaction, but it is an interaction between the red box and the blue box. That's a third law pair of forces, and they don't cancel each other out because they don't act on the same object. And so if you were then going to, say, write a Newton's second law equation for this, how about for the blue box, the acceleration would be equal to the net force divided by the mass, and if there's no other forces on this, then we'd say acceleration is equal to negative Ft. I'll make left be negative, divided by m. And if I did the same thing for the red box, acceleration equals net force divided by mass. Here, acceleration on this one, again, if there's no other forces, would be a positive Ft, force to the right, divided by m. So these two things are accelerating in opposite directions as a result of that one interaction, that one force anyway. If there were additional forces, that would change, of course. But they don't have those two forces, the one to the left and the one to the right, they don't appear in the same equation. So the positive force, the one to the right, appears in the Newton's second law equation for the red box. The negative tension force appears in the equation for the blue box. They don't mix. So we don't have a plus Ft and a negative Ft combining to give us a 0, to give us a canceling out of those forces. Now when we have problems with multiple objects whose motion we have to analyze, we really see the value in understanding this Newton's third law business. So let's say we have block B here, long block that block A can sit on top of. Block B is sitting on top of the floor. and we'll just start it at rest. We're not really going to do much with it, so it might as well be at rest. Block A is on top of it, and then we tie a rope to block A, and we're just going to pull that rope over to the right. And so let's analyze the forces then that are acting on these two blocks, and from there you'd be able to go into Newton's second law and make some calculations for those as well. So first off, block A. And block A is the blue one, has a few forces on it. We've got that tension force to the right, and that one is from the rope. We've got a downward force from gravity acting on block A, and that's caused by the Earth. We'll call that FGA. We've got an upward force from block B that we call a normal force. Normal force, that'll be B on A. And then let's say there's friction in this problem. So we've got frictional force that's trying to keep block A from sliding across block B. And so that frictional force is going to go back this direction. Force of friction, and that again is an interaction with blocks B and A, so that'll be B on A. Okay, then when I draw the free body diagram for block B, we again have a gravitational force, and that's downward force that's caused by gravity interacting with block B, so that's separate from the gravitational force from block A. Let's see, we've got a downward force from block A. Block A is sitting on top of block B, so it's pushing down on block B. That's not a gravitational force, that's a normal force. It's the third law pair for the normal force from block B on block A. So we've also got this force normal from A on B. Block A had a normal force from block B, so block B has a normal force from block A. All right, and then friction. There's friction between blocks A and blocks B. Block A is being pulled to the right, and it's going to try and drag block B along with it, and that's due to friction. We have a frictional force going to the right, and that frictional force is block A acting on block B. And that force will be the same size as the frictional force of block B acting on block A. All right, and then we've got another normal force between block B and the floor. Normal force, and that's the floor on B. Acting upward. We don't really know. There's probably friction between the floor and block B as well, and so that frictional force would act back this direction. Block B is trying to get pulled along with block A, so friction with the floor is resisting that motion. We don't really know amounts for that one or for the normal force from the floor on B, but we can at least say that this force, this force right here, the normal force from block B acting on block A, and this force, the normal force from A on B, will be equal in magnitude, opposite in direction. This frictional force from B on A will be equal in magnitude to the frictional force from A on B. So a few applications for Newton's third law, and you'll have plenty of opportunities to practice.